What we've just seen is that our tries have an asymptotic runtime benefit over our binary search tree or our hash table implementations, and that seems cool. Now, I should note that that is a purely theoretical benefit, that yes, technically the order of growth is constant as opposed to, say, log. I think that in practical applications for any actual data set out there, I'm going to suppose that tries are actually going to be a little slower for operations like get or add, because you have to walk through one character at a time, at least the way we've implemented tries so far. So you might say, well, what good are these things if they're not actually any faster? We spent all this effort, like what's the point of this? Well, the answer is that tries support special operations above and beyond a normal set. For example, prefix matching. So you might ask yourself, what in this set here, what is the key which is the longest prefix of sample? Okay, so A is not a prefix of sample, sad is not a prefix of sample, but same is. So in this set here, the result is sam. So you could write a longest prefix operation for a hash table or a binary search tree, but it's not going to be as efficient as in a trie. Another example, let's say we want to find all the keys that match a given prefix. So what is everything that starts with sa? Well, in this case, it would be sad, sam, same, and sap. And what we'll see is that tries very naturally support these operations, whereas they're trickier to do in a hash table or a binary search tree, and you won't get as good results. Now, it's not just prefix matching. There's other string-specific operations you might consider, but I'm not going to do it in these videos. But our optional textbook, algorithms textbook, does talk about these. Okay, so now that you understand what keys with prefix is, let's try and implement it. Let's try and see what makes a trie good at this. And so as a warm-up exercise, I would like you to try and write a method called collect. And what it does is it gets all of the keys in a trie. So if I call it on this trie, I would get back A, alls, sad, sam, same, and sap. Now this is a pretty challenging warm-up exercise, very challenging, in fact, and a little ill-defined. So maybe give it some thought, but if you're not really sure what I'm even asking exactly, like what does it mean to solve this problem, I'll give you a hint in a moment and a more firmer starting point. Okay, so here's what I have in mind. The collect operation does the following. It creates a list of results x, and then for every character that is off of the root, I'm going to do the following. So basically, root.next.keys, that's all of the characters that follow. I'm going to call my collector helper function, and I'm going to pass along that character in quotes. So for example, if I have the letter A, this will be the letter A in quotes. I will pass along my results list, and I will also pass along the node corresponding to that letter. So I'll get this node here. And then we'll return x when we're done. So now the challenge for you is to write the collector help function and do it in pseudocode. Not real Java, just something kind of like what I have on the slide. And if you're not sure where to start there, think about what happens if the node we're looking at is a key versus not a key as your first step. Okay, so the collect help method I have in mind is as follows. If the node we have now is a key, then we're going to add the string that was given to us. So for example, when we're at the node A, we'd be adding the string A to our results list. And I'll do a little animation in a moment. And then for every character coming off of the current node, we're just going to call collector help, same basic pattern as before, except that now we're going to add that character to the end of the string we currently are building. So for example, when we first start, we're going to call collector help on the letter A. We pass a pointer to this results list x, and then we are going to pass this node as the third argument. So that's why I'm showing it here. So this node for A is the third argument. At this point, we say that this node is a key, so we're going to add A to the list, and then we'll call recursively collector help the string aw, pass along x, and do it on this node. Okay. Now there's one character coming out of here, so we're going to do collector help all, then we'll do collector help alls, and at this point, since this node is blue, we'll add alls to our list up at top. Okay, we're finished with this whole branch, so the recursive call would end up coming all the way up to the root, and then we would call it on the right child. So now we call collect help, give it the string s, x, and this time our node is white, so we don't add it to the results list. then we get saw, and so forth. And after repeating this recursively, we would end up having a, all, sad, sam, same, and sap. So it's a really pretty algorithm. I like it. It's fun. So it's very natural, and it'd be much trickier to do something similar in a binary search tree, or especially in a hash table. Okay, next challenge. Well, now that we have collect and collect help, I want you to give me an algorithm for finding keys with prefix. So in this case, sa should return sad, sam, sap, and same. And so a hint is you can use something from the previous slide. So in this case, the algorithm, to me at least, jumps out at me. But I made the slide, so not so surprising maybe. So in this case, what we will do is find the start node, which I'll call alpha, corresponding to the string you gave me. So here I'm showing it in pink. Then I'll create an empty list. Then for every character in the alpha node's next keys, so in this case D, M, and P, we're going to call collect help on sad, sam, and sap on these respective nodes. So we're basically collecting all of the nodes below A with sa prepended, and that gives us our answer. Another operation you might consider is longest prefix of. I'm not going to talk about it in lecture, but if you like, it will be an exercise you could do in lab. And so there we see that these operations allow us to do something pretty interesting. And so in the coming videos, we'll see how we can use this to actually implement the autocomplete algorithm from browsing the web.